Hello everyone, we'll discuss in this session problems on sieve analysis as well as liquid limit, because we have done the theory. In sieve analysis I think I have discussed only one problem, but in today's session we'll see some more problems on both of these aspects. I think that will close the whole syllabus of module number 1. Okay, we'll go straight away as problem number 1 on sieve analysis. This is taken from July 2018 question paper, question number 1B it is. The data given is the sieve analysis sieve size is given in mm 4.75, 2.0, 1.0, 0.425. We call this itself as 425 microns, or 0.212, 0.15, 0.075 mm, and then lastly the remaining portion which is passing through 0.075 falls in blank pan. 0.075 is referred to as 75 microns, 150 microns, 212 microns, 425 microns, and so on. So weight retained on each of these sieves is given in grams, it is mentioned. And what is said in the problem is 500 grams of dry soil was subjected to a sieve analysis. The weight of soil retained on each of the sieves is given. Plot a grain size distribution curve and determine the following. Very specific they are in the question paper. Percentage of gravel, coarse sand, medium sand, fine sand, and silt clay fraction as per IS 1498-1970. Then number 2 is effective size, number 3 is uniformity coefficient, 4th is coefficient of curvature, and then you have to comment on gradation of soil. Okay, we'll do the calculation and then plot the data. So here I have worked out 4.75 up to pan. The weight retained is given, it is 10 grams, 165, 100, 85, 40, 30, 50 and 20. I think that is the data. 10, 165, 100, 85, 40, 30, 50, 20. Okay, now cumulative weight retained. Cumulative weight retained is summation of 10 plus 165 for 2 mm sieve, because weight retained on 4.75 is 10 only. Weight retained on 2 mm is 165 plus 10, because if you see the whole soil, what happens is not only 165 but even 10 also stays above 2 microns, 2 mm. Likewise, if you sieve the soil through 1 mm, the weight retained will be 100 as well as 165 as well as 10. So like that. So cumulative weight retained will be, the first data will be as it is, second will be 10 plus 165, 175. Next will be this 175 plus 100, 275, plus 275 plus 85, that is 360, plus 40 would be 400, plus 30 is 430, plus 50 is 480, plus 20 is 500. So whole of 500 grams of soil is like that. Now this is called cumulative weight retained on any of the sieves. What it means is, for example, 425 microns, the total soil, if you sieve it through 425 microns, what is the amount of soil which will be retained on 425? It will be 360 retained on. So this is cumulative weight retained. Now percentage cumulative weight retained, out of 510, but if you work out for 100, how much it will be? Like that you have to work out. So it will be simply for 500 it is 10, but for 100, or it will be divided by 5. Hope you can understand. Let me write for this. 10 is given, and this 10 is for 500, but for 100 we want, that is what is percentage. So if you just look at this, these two zeros will getting cancelled. You have to divide by 5. That is what we have done everywhere. If you go on dividing by 5, because of this reason, that is important, not just divide by 5, you will be getting cumulative weight retained. So cumulative weight retained is 2%, 35%, and so on. Now what is the percentage finer? That will be 100 minus 2, because cumulative weight retained above 4.75 is 2. What is passing through? What is finer than? It is obviously 100 minus 2, 98. Like that, everywhere it is 100 minus all these numbers. You'll be getting a percentage finer. This is what is required for plotting the grain size analysis and then sieve size. Okay, now if you take a graph and then plot it, I'll explain you the plotting. Look at the graph. I have taken purposely 0 label over here so that I can write a lot of material over here. So make a note of this. So 0 is written here, and then as far as y-axis is concerned, it is percentage finer, and it is equally distributed, 10, 20, 30, and so on, up to 100%. So as far as y-axis percentage finer is concerned, there shouldn't be any difficulty. But for x-axis, that is sieve size of the sieve. So this, if you want to plot, you have to take care. So what I have done, I'll explain you here. The first one I have taken 0.01, and you can just see here there is a jump over here. Over here there is a jump, over here there is a jump, and so on. So this is multiples of 10. So it is 0.01 multiplied by 10 would be 0.1, multiplied by 10 would be 1, multiplied by 10 would be 10. So this particular point is for 10, and so on, right? Hope you have understood. Now 0.01, once you have, the next line will be 0.02, 0.03, and here 0.075 is between 7 and 8. Then you have got 0.08, 0.09, then comes 0.1. Obviously 0.1 is here, 0.2 would be there, 0.3 would be there, 0.4 would be there, 0.425 would be there, 0.5, and so on. 0.9, this will be 1, this will be 2, 3, 4, 4.75, 8, 9, 10, 10, this will be 20, this will be 30, and likewise you have to plot the graph. Now let us plot for 4.75. If you take 4.75, the percentage finer is 98. So here it is 90 to 100. So 98 would be that particular point. Okay. Similarly for 2 it is 65. So 2 is there, 65 is there. So obviously this is the plot. So likewise I have plotted all of them. You can make 1 mm. Where is 1 mm? 1 mm, and then this is 45%, and if you come down 0.15, it is 14.15, it is 14% over there. This is 0.212, that is 20%, and 0.075 we have got 4%. Okay, this is how to draw the graph, and draw a smooth curve which is passing through all the points. You cannot average the curve. That is what is the point to be noted down. So you have to draw the curve, a smooth curve which is passing through all the points. Now what is asked is effective size. They have asked effective size is nothing but D10. So how to find out D10 is you have to uh, go to 10% line, move this direction, come to the curve, go down, and what is the size? And this is 0.1, this is 0.2, so this will be 0.12. So 0.12 mm I have written. Okay. Now similarly 30%, D30. So 30% you catch on, move horizontally, go here, and then 30% go down, and then what is the size, that you have to note down. So here it is slightly more than 0.42, but below or less than 0.5. That's why I have written D30 as 0.49. And D60, if I go down over here, this will be something like 1.6 or 1.7. I have written at 1.6 because 1 is here, 2 is here. Now 1.1, 2, 3, 4, 1.6 is whatever I have. D60 I have noted down. Okay. Now once you find D10, D30, D60, you know Cu is equal to D60 by D10, that is 13.33. Cc is D30 square divided by D60 by D10, that will be equal to 1.25. Okay. Now this is the data. You cannot comment this unless you know the percentage. Let us work out the percentages. Now what is percentage of gravel? The particles which are greater than 4.75 are gravel. Now particles finer than 4.75 are 98%. Obviously the gravel will be 2%. So percentage of gravel is 2%. Now percentage of fines. Fines means the particles which are less than 0.075, and that is 4%. So percentage of fines is 4. So 2 and 4, 6 gone. In between 0.075 to 4.75, this is the whole range of sand. So what is the percentage? Obviously 100 minus 2 minus 4, that is to say 94% is percentage of sand. So looking at the percentage of sand, we can say that the whole soil is coarse grained soil and it is sand. Classification is sand. Now if it is sand as decided, and then if Cu is greater than 6, Cc is between 1 and 3, we can say that it is well graded sand. So for sand it is a well graded sand, because of that we can clearly write it down that SW would be the classification symbol. So that's the thing that is asked. Hope we have done everything. Effective size, uniformity coefficient, gradation of soil, well graded sand we have said, and plotting etc. we have done. Okay. We'll go to the next slide. Here the data is given slightly in a different manner. A soil sample has 98% of the particles finer than 10 mm. So they have said it is 10 mm is the size, percentage finer is 98%, directly given it is 98% is percentage finer. A soil sample has 98% of the particles finer than 10 mm. So it is simply percentage finer. What we can say is, okay. Then there is a comma. 59% finer than 1 mm. So if I say 1 mm here it is 59%. And 24% finer than 0.1 mm. So if it is 0.1 mm here, 24% is the data, 0.1 mm, and 11% finer than 0.01 mm. So here 0.01 mm, and correspondingly about 11%. Now draw the grain size distribution curve and calculate percentage of the gravel, sand, silt and clay. Also calculate CuCC and report the gradation of soil. Okay, the data is of not full length as we have done in earlier problem. So what to do now? You have to plot the graph. Okay, I have taken the graph. Now just see here, in the same manner I have plotted 0, 10, 20, 30, 40 and so on y-axis, which is percentage finer, and then I have taken this scale, horizontal scale here. You can make out here, this one is 0.01, this is 0.1, this is 1 and this is 10. That's how the sizes are taken in multiples of 10. Okay, now first one, 10 and 98, 10 mm, 98%. So where is that 98? You can just see here, 98% is plotted. This is the point that I have plotted. Because it is 90, so you got 5 blocks, each one will be of 2, 98 would be there. So 98 and corresponding to 10 mm. So with 1 mm it is 59%. So with 1 mm it is 59%. So 59 is somewhere there in between 58 and 60, 59. So 0.1 mm, 0.1 mm, 24%, that is the point. You can just check the plotting here also. Now here 0.01 mm to 11%, 0.01 mm, 11%. So that is the point. Okay. Now you draw the curve. I have drawn a smooth curve which is passing through all the points, right? Okay. Now they say you have to calculate the percentage of the gravel. Now what is percentage of gravel? Percentage finer than 4.75 is 90%. See, look here, 4.75 I have got. I'll go up there and try to find how much is the percentage. It is now 90%. So from the graph I can find out. So going from this way, come up to this point. Okay. Now this point is on the graph. Now you go this way, 90%. So percentage finer. This is percentage finer. Percentage finer than 4.75 is 90%. So what is the percentage of the gravel? Now if you just see here, it will be 100 minus 90, that is 10%. So percentage of gravel becomes 10%. Okay, percentage finer than 0.075 over here, 0.075. So percentage finer than 0.075, if I go up 0.075 and then try to find out what is the percentage, it is slightly above 20, between 20 and 22, that's why it is taken as 21. So percentage finer than 0.075, I have taken it as 21%. Okay, so percentage of fines, clay and silt are nothing but 21%. The percentage of gravel is 10, percentage of fines is 21. So what is the percentage of sand then? Percentage of sand would be 100 minus 31. So percentage of sand is given as 100 minus 31. 100 overall percentage, of that gravel is 10%, of that fines is 21%. So leftover thing is 69%. So 69% would be the sand. So 69% is the sand. So overall, because the percentage of the sand is more, I can say that the soil is sand, or the classification would be sand. Now percentage of fines is more than 12%, it is 21%. So fines, if they are more than 12%, your classification symbol would be S, M or SC, right? You will not be able to judge this straight away. Okay, so that is what one can decide at this stage. And CU and CC, if you work out, we have D60, D10, D30 worked out from the graph. You can just look over. So D60 is 1.1, it is 1.1. D10 already done, it is 0.01. So D60 by D10 CU is 110. Similarly CC, D30 square divided by D10 D60, it is 3.46, more than 3. So it is not well graded. Anyway, this is not a matter at all, because anyway it is going to be SM or SC. The given soil is poorly graded, right, as far as this is concerned. Classification is sand, but symbol will be SM or SC. To decide M or C, we should have data about plasticity index. Now if plasticity index is greater than 7, then I would fix SC. If IP is less than 4, I would call it as SM. That's how the classification has to be done. So as far as gradation is concerned, it is poorly graded because it's not satisfying both the conditions of CU and CC as far as sand is concerned. Because for sand, for well graded, CU has to be greater than 6 and CC has to be between 1 and 3. This is coming to be 3.46. So it's not well graded, but because percentage of fines is more, it will be either silty sand or clayey sand. So SM is silty sand, SC is clayey sand. We'll go further. Okay, here liquid limit problems are there. Couple of them I have solved from the question paper. The problem from the question paper reads this way: a liquid limit test was conducted on a soil sample whose plastic limit is 24%. The plastic limit is given, right? So WP is given. The following results were obtained: number of blows required, water content. Number of blows in the sense it is actually number of drops it should be. It is liquid limit by Casagrande's method. What they have said is draw the flow curve and determine liquid limit, plasticity index, liquidity index, consistency index. If the natural water content is 28%, toughness index, flow index, all the indices are asked. Okay, for that you have to find out first of all liquid limit. Now how to do that? We'll plot the graph. Okay. The plotting is again on the log scale here. So you should remember that liquid limit test, Casagrande's method, you have to plot the graph on semi-log paper. Semi-log in the sense vertical axis it is uniform scale, but horizontal axis it is multiples of 10. So here I have started with 10 itself, and then it goes to 10 into next 10 is 100, right? Next 10 would have been 1000. Next 10, or left side if you go, if it is 10, here would have been 1, would have been 0.1, would have been 0.01 and so on. So I can start at any power of 10 and then increase it or decrease it as per the requirement. So here my blows, number of blows are 12 to 34. Because of that it will be 12 to 34 somewhere there. So 10 to 100, that is what is the range. Now percentage, this is 56, 52, 50, 45. So I have started with 30, 40, 50 and 60 so that I can plot all the water contents. Okay, now what is the first point? For 12 number of blows, 50%, 56%. So for number of blows 12, I have marked it here 12. 56%, this is 50, this is 55, 56%, that is the point. Okay, now similarly for 18, this is 10 and this dark line is 20, so that is 18. For 18 it is 52%, so it is 52%. Then for 22 it is 50. For this is 10, I mean this is 10, this will be 20, this will be 30. Now between these two all the points are 22, so 22 I have marked a point there. For 22 it is 50, and then for 34 it is 45, so 40, 45. So these are the 4 points plotted, and obviously in this graph it is a straight line curve, right? You have to draw that whole straight line and find out the point of intersection on y-axis also. Okay, now what is the first thing required is liquid limit. Now how do we find? In liquid limit we said that in Casagrand's method, the water content corresponding to 25 blows or 25 number of drops is liquid limit. So I'll choose 25. I go up a graph, hit the curve and move backwards or leftwards, find out the percentage. It is 48.5%. So I report liquid limit as 48.5%. Okay. Now once I know liquid limit, because plastic limit is given, I can calculate liquid limit minus plastic limit as plasticity index. So plasticity index comes out to be 23.5, say 24%, or 0.24 flow index. Okay, so what is flow index? Sorry, flow index is nothing but the slope of the curve. I'm sorry, flow index is nothing but slope of the curve. Now how to find out the slope of a curve? You can choose any 2 points, and best would be 110. So log 100 minus log 10 is on y-axis, correspondingly W1 minus W2. So here it is 57.5, here it is something like 34. So the difference is 57.5 minus 34, that is 23.5 divided by 1, say around 24. That is what is flow index. Okay, this line is called flow curve, and plasticity index is WL minus W10, I mean WL minus WP, IP, you know all this now. WL is 48.5 minus plastic limit 24, so this also comes out to be 24.5. so plasticity index is 24.5. Now liquidity index, consistency index, etc. you can solve, because I have already solved in earlier problems all those things. Those formula you have to use, right? The new matter over here is how to plot the graph and then how to find out liquid limit. Okay, we'll go further. Okay, this is one more data. The following data was obtained from liquid limit test on a cohesive soil. Number of blows are given, moisture content is given, plot the flow curve, determine flow index, liquid limit. If the plastic limit of the soil is 18.5, what are the plasticity and toughness indices? Okay, here the graph is done. Again I have chosen 10 and 100 on the x-axis, 10, and next jump is 10 into 10, 100, and this is 10, 20, 30, because percentage is up to 36%. That's why I have taken the liberty to plot it 10, 20, 30, 40 up to 50. Now if you plot for 40 it is 25.5, for 40 it is 25.5, likewise 35, 28, 35, 28, and so on. There are 4 points I have plotted and drawn the curve like that. Okay, now see that 100 and then 10, if I choose, those are the values I have highlighted. Now from the graph, liquid limit is, how do you find liquid limit? It is water content corresponding to 25 number of flows. So I have chosen here 25, I have gone up the graph. Here I'll go leftwards and then see that it is 31%. So liquid limit is reported as 31%. Plasticity index is WL minus WP. WP is given, plasticity index is given. So IP is 12.5%. Flow index is slope of the curve here. So obviously it is 40.5 minus 16.5. So you can just see here 40.5, this is 16.5, divided by log 100 minus log 10, because corresponding to these red lines I have taken. So 110 log 100 minus log 10, that is, it will become 1. So it is simply 40.5 minus 16.5, that is 24. That is the flow index. Toughness index is IP by IF. So if I calculate, I will be getting 0.521. Okay, I think with this we'll stop. Thank you. Here we have finished the module number 1. I have solved number of problems. You also should practice. It's a big chapter which builds a good foundation for you. All other things are developments depending upon all these properties. Okay, thank you.